Many thanks to Irina and others for organizing this conference. It's been very stimulating. And it says here that am I audible? Is there any issues with my sound?
We can hear you.
Okay. And it says here I'm an independent researcher, but in case anybody likes my work and they want to make me a dependent researcher, meaning give me a job, I would be very happy. This is work which is done in collaboration with Lynn Tequeira de Souza, who is a very, very talented student at the Universidade Federal de São Paulo in Brazil. And if anybody takes her on as a PhD student, they will be very happy. So this work first came out on arXiv last year, and earlier this year, a few months ago, it was accepted in Annals of Physics. There's also a GitHub repository of the paper where you can access the contents. Now, I'm going to first give a brief motivation overview of strings and loops. Then I'm going to discuss how minimal area arises in loop quantum gravity, present a modified bosonic action for the Nambu-Goto string, talk about the relationship to bimetric gravity and the bimetric string, and then show that this area correction can actually be interpreted as coming from the Karl-Bromond field, and finally present a model for classical holography arising from a gauged model of the bosonic string. So, and then I will have a dedication. And if anybody wishes to ask me any questions, they're welcome to. So string theory, as everybody knows, is the dominant paradigm. And as probably everybody also knows, its origin lies in the analysis of rigid trajectories, which led Veneziano to propose his form of the amplitude. And from this, various people, including Nambu, Susskind, and Nielsen and others, proposed a string interpretation. But it wasn't until Nambu and Goto that we finally had a bosonic action. Now, here T is the string tension, and this is the area of the string world sheet. So the Nambu-Goto action is very simple. It's just the area. And this string is embedded in some background D+1 dimensional manifold. And the embedding is given in terms of, one second. The embedding is given in terms of some fields, x mu, and the worldsheet metric can be pulled back using these fields, as you might know. So the point here is that, well, string theory is grounded in particle physics. And it doesn't really care too much about the symmetries of general relativity, such as diffeomorphisms. Whereas loops emerged from general relativity. And after many decades of endeavor, people were unable to quantize general relativity using standard procedures. And they turned towards the Hamiltonian approach, which is the Dirac constraint approach. The issue is that the that ADM formalism gives constraints which are highly non-polynomial, and there's really no hope of quantizing them. Now, in order to understand how to proceed, we can look at the difference between general relativity and the other forces. General relativity is the theory of bimetric, whereas the other three forces are theories of gauge connections. So democracy might suggest that, well, maybe the other three are in the majority, have something to say about it. And Amitabh Sen in 1982 was the first person to write down general relativity as a theory of a connection. And in the acknowledgement section of his paper, he mentions Ashtekar as being specially indebted to Abhay Ashtekar. But there were problems with his work, and it was not as complete as it could have been. And Ashtekar in 86, 87 presented the final formalism, and he showed that gravity can be written as a connection theory of an SU2 connection and a non-abelian field, electric field, whose kinematical phase space is precisely the same as that of Yang-Mills SU2 gauge theory. And the physical Hilbert space, the physical phase space is obtained by imposing the constraints of general relativity. So I suppose most of you are familiar, if not all of you are familiar with how to write down the Einstein-Hilbert action in Palatini formalism. But I just want to state that, well, it can be done in a very straightforward manner by introducing a gauge connection, SL2C gauge connection, and orthonormal tetrad basis. And then what we do is we proceed with a 3+1 decomposition. And after doing that, we perform this canonical transformation into what are known as Ashtika variables. And when we do this, we obtain this gauge connection, this capital A, which is my cursor visible on the screen? I can't see my cursor. One second. Okay, I can't see it, so I hope that's not a problem. And this Ashtika connection is a genuine SU2 connection. And we have this conjugate momentum, which is related to the inverse triad. And the constraints take a very simple polynomial. This allowed people like Rovelli and Smolin and others to quantize the gravitational phase space for the first time and provide a complete non-perturbative picture in terms of what are known as spin networks. And one of the most fundamental predictions of loop quantum gravity is the existence of a minimum quantum of area. And again, it's very important to emphasize that this is a prediction, not some ad hoc addition to the framework, as is often suggested by people in other talks. So we know that the area is given by this expression. It's just the integral of the volume form of the surface. And we have this canonical momentum, which can be written in terms of the inverse triad and the square root of the determinant. And using this, we can express the area in terms of this canonical momentum. So this is a classical expression. And to quantize it, what one does is, well, instead of working with states which are functionals defined on the entire three-dimensional spatial slice, we use our intuition, which comes from gauge theories, and work with states which are functions of holonomies and fluxes. So in the general description of states is in terms of graphs, where each edge is labeled by a holonomy. And the wave function is a function of these holonomies in terms of so-called cylindrical functions. And once we have this holonomy, we can ask what is the action of the momentum operator on the graph state. And that will reduce ultimately to the action of the momentum operator on a single holonomy. If you look at the expression for the holonomy, the derivative will simply pull down a copy of the generator tau of SU2. And when you quantize it, that tau will simply be replaced by the angular momentum operator J for the corresponding representation. And so the momentum operator takes a very particularly simple form when quantized on a single edge, which pierces a surface. Now, as an aside, I just want to note that I noticed that in a talk given yesterday by Katif, he talked about Wilson-9 networks. And well, Wilson-9 networks are exactly the same, literally exactly the same as these graph states of spin networks. Only the graph states were discovered about 15, 17 years before Wilson-9 networks. So now, finally, we can use these expressions to determine the area of a surface. And we know that the action of the momentum operator will just give us a copy of the angular momentum. So two of these will give us simply the Casimir of SU2, and the smallest eigenvalue of this is non-zero. So this is a fundamental prediction of loop quantum gravity, that the smallest measurable area in quantum gravity is of order Planck length squared. Now, There are many successes of string theory, but there are also many issues. And so one might think that, well, maybe there are some insights that one could use from another field, such as loop quantum gravity, because loop quantum gravity also has many successes, such as loop quantum cosmology, the successful prediction of black hole entropy by Rovelli, coincidentally in a paper which came out before the Qumran-Waqfa paper, which is cited by literally everybody as the string theory demonstration. But Rovelli showed that you can equally well do it using loop quantum gravity techniques before them. So the notion is that, well, can you maybe think of a possible relationship between these theories? And the main problem with loop quantum gravity is how to relate this discrete quantum geometry with the continuum field theory that we all know and love. And the idea I had is that, well, maybe string theory can serve as a buffer, as a sort of an API layer between the underlying quantum geometry and our observable physics. So in October 23, I had this idea that, well, what is the simplest way to modify? Because I was just thinking, well, I don't know what the exact microscopic dynamics is. Let me try and see if I can come up with some phenomenology. And so I came up with this modification of the Nambu-Goto action by simply adding a constant term under the square root, so that even if h went to 0, the total area would never be 0. And I introduced this constant k, which is the ratio of the string length to the Planck length. And the assumption here is that this describes a string which is propagating on a background whose geometry is described by spin networks. And these spin networks puncture the string world sheet and give it area. And we are looking at this string at a scale that is large, much larger than the scale of quantum geometry. And so this k has to be much less than 1. So this is like a weak coupling limit. Of course, people can take issues with this interpretation. Now, one can expand this integrand because k is much less than 1. And if you expand this, you find that the action becomes a sum of two terms. One is the Nambu-Goto term, and the other as this inverse determinant of the metric. And this has a form which is actually, which appears very often in the loop quantum gravity literature in the form of inverse triad corrections, which actually leads to singularity resolution at the Big Bang, for example. So this action turns out to be very nice. It might seem artificial on first sight, but it's covariant. It respects the usual symmetries that one would like it to have. And more importantly, when I write down this action as a sum of these two terms, and I'm ignoring the higher order terms, by the way, this looks like a sum of an action for a world sheet which has two different metrics. One is the metric h, and the other can be thought of as it is the inverse of that metric, because the determinant of the inverse is 1 over the determinant. And this action has a very interesting property that if you map k delta to 1 by k delta and t to t prime, the action remains invariant. So this implies, since k is much less than 1, this implies that t prime is much less than t. And that means you have a duality between strong and weak coupling between world sheets of large area and small ones, large string tensions and small string tension. This is very reminiscent of both the S dualities and the T dualities that are present in string theory. And so, it's obviously something to look at, but we still have to delve deeper into what this would imply for the phenomenology. So investigating further along the line of thought that, well, is there a situation where one can write down a physics with two different metrics? It turns out that, well, this is very well known. This is called bimetric gravity. It was first discussed long back in the 1940s by Nathan Rosen, Einstein's collaborator, and Piers Pauli. And they proposed an action for massive gravity. But the issue with the massive gravity action is that it has a Boole-Ware-Desert ghost at next to linear level. in the perturbations. And then in 2011, 2010, Diram, Gabardadze, and Tolley, in what is a seminal achievement, showed that one can write down an action which is ghost-free to all orders. It is non-perturbatively ghost-free. And Hassan and Rosen showed that uh, you can write this down as an action for two arbitrary metrics, here shown as G and F, plus an interaction term between the two. So taking inspiration from this, I thought that, well, is there a concept of a bimetric string? There are many works which consider bimetric gravity in the context of string theory, but none which actually have something like a bimetric string model. So there are different ways in which one can think of a string with the two metrics. The first is that one could think of a string which is described by two different embedding fields. And the same bulk metric. So the pullback of that same bulk metric with respect to two different embedding fields gives you two worldsheet metrics. The other alternative is that you have two different bulk metrics. Now, I like the second approach better because it relates more closely to the bimetric gravity in the bulk and with only one set of embedding fields so that you only have one string worldsheet. But now you have two different metrics again on the same worldsheet. And I've written here the action in Polyakov form for both of them with an interaction term. And PB stands for Polyakov bimetric. And if you assume that the interaction term is 0, well, this reduces to this bimetric form, where H here does not as yet have any relationship to G. They are independent metrics. So now it turns out that, well, what we would like to do is we would like to start with something like this, where H and G are independent, and understand whether we can obtain a form of this kind where H is the inverse of G. Now, this requires that the determinant of H should be equal to delta square by G. And we can achieve this by setting H and HAB to take this form, where GCD with the upper indices is the inverse metric, and delta AB is a tensor which we have introduced, and we'll see what it does. Now we can write down the inverse metric in terms of epsilon tensors. This is an expression for the determinant of any matrix. And using the expression for the pullback, we arrive at this identity, which should be 0, which is 0. But it depends on the form of delta. And the simplest way in which this can be 0 is by setting delta to be equal to root of delta times the epsilon tensor. And so what this suggests is that the quantum of area that we have introduced is related to the pullback of the bulk Karl-Bramond field, which is the antisymmetric field which couples to a string theory in the bulk to the worldsheet. Now, as far as solutions of our model is concerned, we obtain the usual modes, with the difference being that in the exponentials, because my cursor is not working, I can't really point it out. In the exponentials, you have an extra term. Sorry, the energy is modified, and instead of being linearly related to the momentum, there is a mass term mu, which depends in a complicated way on the quantum of area delta. When we impose the constraints coming from the stress energy tensor of the worldsheet, we find that instead of the usual Virasoro algebra, we have two index Virasoro modes which satisfy these conditions. And in addition, the mode coefficients alphas, they vanish for n greater than d minus 1, where d is the dimension. So this is a reflection of the underlying discreteness discrete structure because you would expect that it would impose some kind of a cutoff on the modes. And there are more aspects of P calculation that I could show you, but again, I'm limited in time. So I'll go to the last section, which is classical holography. So we would like an understanding of how the background geometry described in terms of a spin connection. So we have a bulk manifold. The bulk manifold has graphs living in it, which encode the geometry of that manifold. And there's a world sheet which is propagating. And the spin connection should couple to the world sheet in some way. So let's say that we start with the Polyakov action. And we ask a graduate student, well, how would you couple this to a gauge field? Now, in the string theory literature, of course, people have studied coupling of background gauge fields to strings as far back as the 60s and 70s. But what I'm asking for is something different, right? Instead of adding a term which corresponds to some gauge field, I'm asking how the gauge field can be introduced within the action itself. The naive thing to do would just be to replace the partial derivatives with covariant derivatives with respect to some gauge connection. But a more experienced researcher, let's say the student's advisor, might say that the embedding fields are space-time coordinates, not vectors transforming under a local gauge group. So how would you implement this formally? So these coordinates, these embedding fields, they satisfy the invariance under translation and Lorentz transformations, assuming that the background is globally flat, which is what is done in nearly all treatments of string theory. But of course, we don't want to do that. We want to talk about strings are propagating in arbitrary curve backgrounds, because how else can one really say that you are studying quantum geometry if you only work with flat backgrounds? And so the idea that we came up with is that, well, let's look at the gauge theory, but with the gauge group being the Poincare group, which is a semi-direct product of translations and Lorentz transformations. But now there is an issue, and according to my timer, it says I have 2 minutes left, but in case anybody wants to cut me off, that's also fine. But I only have a couple more slides to go. So the issue is that in order to be able to implement infinitesimal translations in addition to infinitesimal Lorentz transformations, because now we want to gauge these embedding fields in some way, we have to introduce a dummy coordinate x of r, which is written in the last line. So now our bulk manifold, instead of being d plus 1 dimensional, becomes capital D plus 2 dimensional. And I've called this the Einstein-Cartan string for obvious reasons, for those who are familiar with the concept of Cartan geometry. And our expanded coordinates have this form where, as of now, I have set x of r to be a constant and equal to 1. Now, this x of r plays the role of a scaling parameter. If you move away from 1, you will have to scale the other x new coordinates accordingly. But if you keep xr to be fixed, then what you're doing is you're fixing a submanifold of your d plus 2 dimensional manifold. So again, the picture that I want you to think of is ADS geometry with some submanifold, which doesn't have to be the boundary. It could be something at some finite cutoff also. And so finally, we end up with this gauged Poincare Polyakov action, where GAB is now the metric of the D plus 2 dimensional bulk geometry. And what the picture is the following. So, okay, well, first let's expand out this action We have in the previous expression, we have G of capital AB. So this is a metric defined on the D plus 2 dimensional manifold. And so it has mu components, mu components, mu r components, and an rr component. And so when we expand it out, we will get three terms for this action. The first term will be the mu component as usual, but again with the coupling to the gauge field. Then there will be these interaction terms between the mu and r components and between the rr components. Now, what this suggests is that in analogy with what happens with D-branes, which is that when you localize the endpoints of a string on a submanifold, then that causes that submanifold to become dynamical, right? It's no longer a static surface, and that's how D-branes come about, as was discovered by Polchinski, Dye, and Ley, and then later by Polchinski. So the picture here is that your string is mostly living on a normal space-time, D plus 1 dimensional space-time, but fluctuations of this coordinate XR can cause the string to come out into this bulk. And so again, this is very, very similar to what one looks at in ADS CFT, where you have strings whose endpoints are glued to the boundary and which are propagating in the bulk. But the difference being that here, everything is at the level of the classical action. There's no need to go to the quantum theory. So in conclusion, we have introduced a new string action, which has an assumption of an underlying quantum of area. This area correction can be related to the Karl-Bromond field. I have presented a bimetric string action, which is something new and has not been studied before. The solutions of this model mix the left and right moving modes, and their quantization results in anomaly-free Virasoro-Klein-Gordon algebra. Again, for why this name is being used, Virasoro-Klein-Gordon, I urge you to refer to our paper. And then finally, we constructed a gauge string action, which imposes local Poincare symmetry and gives a local and classical picture of love.